In the last video, then, we saw that inside a shrinking nebula, in the hottest part of the nebula at the very center, the particles end up moving so fast that these protons get within femtometers of each other, where the strong force can hold them together, and we fuse hydrogen nuclei into helium nuclei. But the process is actually a little more complicated than that, because if you remember, this is actually the notation for helium. This number is the atomic number, which tells you 2 protons. This is the atomic mass, which tells you the number of protons and neutrons. To have a mass of 4 with 2 protons, you also need to have 2 neutrons. Where did the neutrons come from? We haven't said anything about neutrons flying around inside the core of this protostar, and in fact there are no neutrons there. So where do they come from? Well, here's where we need to go back to a modern understanding of particle physics and forces. Because remember that the difference between a proton and a neutron is what type of quarks make it up. And in fact, the difference really is 1 quark. Both of them have an up quark and a down quark. But a proton has, as its 3rd quark, it has an up quark, whereas a neutron for its 3rd quark has a down quark. So we could actually turn a proton into a neutron or vice versa by flipping one of these quarks. And in fact, that's what happens. 4 protons will fuse like this, and then the nuclear weak force, remember, which is the one that affects quarks, will actually flip a quark in 2 of the protons and turn them into neutrons. And that's really important because remember that all 4 of these protons are repelling each other with the electromagnetic force. They're also holding each other with the strong force. But in fact, 4 protons repelling with electromagnetic force could not be balanced by 4 protons attracting with the strong force because of the distances that are involved. But by turning 2 of those protons into neutrons, neutrons, remember, also exert strong force, so they will help to hold the nucleus together, but they don't experience electromagnetic force because they're neutral. They have no electric charge. And so there's no repulsion here. You've actually, by turning these protons into neutrons, you've reduced the electromagnetic repulsions by half, but you've kept the strong force attractions the same. And so without the weak force turning protons into neutrons, you actually could not create any larger nuclei. The universe would be only hydrogen. Now, the process is a multi-step process because the chances, even in the sun, in the center of a star with so many protons flying around, the chances of 4 protons colliding at exactly the same instant with exactly the same energy at exactly the right angles is very, very slim. In fact, the process happens in multiple stages in something called the proton-proton chain. So what happens here, you can see, is that 2 hydrogens will collide to form a heavier hydrogen nucleus. It's called a deuterium with 1 proton and a neutron. In the process, it releases a little neutrino that balances all the mass. It releases a little neutrino and a positron, which is a particle of antimatter. We didn't have a chance to talk about that, unfortunately. But here is my deuterium. This happens twice, so I have 2 deuterium nuclei. Another proton can strike that deuterium, release a gamma ray, a bit of energy, pure energy, to form a helium-3 nucleus. This process happens twice, and then the helium-3 nuclei smash together. 2 of the protons are released, and you end up with your helium-4. But how does this provide energy for the star? That will be the topic of the next video.